Hi everybody, my name is Sarah Landgraf, and I'm going to be talking today about the beginnings of Greek mathematics. And before I get started, as far as the origin of Greek mathematics goes, it's not super well documented. The civilizations before the Greek one had built incredible things, like, for example, a four-story palace with successful drainage, which is an amazing feat. But they didn't really leave behind a lot of mathematical documents. So here is a world map just for reference. And here's Greece, surrounded by water, so that means lots of ports and lots of influence from other places. And then also we are going to be talking about Samos later. And that is a Greek island, but it is right by Turkey. So Greek numerals. They came from the Phoenicians around 900 BC, and they were decimal based on powers of 10. And they used the alphabet for their numbering system. So there were three symbols, let's say Vau, Kappa, and Sampi, and they were used for mathematical purposes but fell out of use. And they didn't have a number for zero, just a symbol. And then as far as representing larger numbers, from 1,000 to 10,000, they would put a comma in front of the number to represent 1,000. And then for numbers larger than 10,000, they used a symbol M to represent 10,000. So like we use exponents, they would say M to whatever times the number that they wanted to represent. And that would be how they did that. And here's a little visual for us. And some of those might be a little familiar. Like I see theta down there in the bottom left-hand corner, and some other familiar ones as well. So back to Samos, the water tunnel at Samos. So Samos was a Greek island in the 6th century BC, and they dug a tunnel straight through limestone that was 4,000 feet long. And this was to provide the city with a secure water supply. And so what they did was they dug from the north and south sides of the island and met in the middle. And they would have met exactly in the middle, except for the north had to move around something. And so we're not quite sure why they moved. It might have been that they were avoiding some water coming into the tunnel or some especially soft ground. But as far as the floor heights went, there was only a 60 centimeter difference at the junction from the north and south sides, which is crazy because 60 centimeters is not a lot. And this was at a time where they didn't have a mathematical compass, and they didn't have surveying instruments or topographical maps. And really, they didn't have much written mathematics either, because Euclid's Elements was written about 200 years later. So this is an incredible feat. And I actually read this really interesting article about these men here on the left who were trying to figure out how on earth they could have done this. And there were some ideas, but their suggestion was that they used a leveling tool. It was a large wooden bow, and it was, I think, 8 feet on both sides, and they would lift it in the center with a rope. And so then you could see if the elevation was the same if the bow lifted up at the very same time. If there was one that lifted up before the other, then they could see that the elevation was different. And so then they would stack rocks or dirt or something and make that elevation the same so they could mark it for 16 feet intervals. And so their suggestion, as we see here on the picture on the right-hand side, is that they, instead of going over the hill or small mountain, they went around by measuring the elevation and keeping it the same. And that's how they got so close, within 60 centimeters of each other. And if they did this strategy, they would only have to make major turns about 6 times. So they think that's an easier and more probable suggestion than some of the other things that have been suggested over time. I did want to talk about Thales of Miletus, who was a Greek mathematician, astronomer, and pre-Socratic philosopher. He is credited with being the kind of the start of proper Greek mathematics and also with developing the scientific method. And his way of proving things was more of making a claim or a statement and then showing lots and lots of different examples. And then if there weren't any major contradictions, then he would basically say they were true. And so his talents were more with characteristics of lines, angles, and circles, as opposed to the Egyptians, who were more skilled in orientation, measurement, and calculation. And so that geometry was introduced into Egypt, and then Thales learned about it when he was visiting Egypt, and then he brought it back to Greece. So here are some theorems that are attributed to Thales, and I know you guys can read, but I'm auditory, so it helps. So the first definition, a diameter of the circle is a straight line drawn through the center and terminated in both directions by the circumference of the circle, and such a straight line also bisects the circle. Proposition 1.26, if two triangles have the two angles equal to two angles respectively, and one side equal to one side, namely either the side adjoining the equal angles or that subtending one of the equal angles, they will also have the remaining sides equal to the remaining sides, and the remaining angle equal to the remaining angle. This is very wordy, but basically he's talking about how he measured the height of the Pyramid of Giza. And when he was visiting Egypt, he would wait until the sun was at such a position where the height of his shadow was the same height as his actual height. And so he calculated what time of day that was. And then when that same time of day hit, he measured the shadow of the pyramid. And that's how he was the first one to figure out exactly how tall it was. And then the last proposition here, the angle in a semicircle is a right angle. And so Aristotle talked about this as well. And he would ask, why is the angle in a semicircle always a right angle? And he would describe the conditions necessary to make this true, but he didn't really get any farther than that. We also have Thales' theorem. If A, B, and C are distinct points on a circle, that's basically a special case of the theorem below. And this special case meaning that the largest angle is 180 degrees, so it makes up the diameter. And then the smaller angle, the angle ABC in our little diagram, is going to be 90. And here's the proof for that. If you guys can't see in the upper right-hand corner, it says since OA equals OB equals OC, triangle OBA and triangle OBC are isosceles triangles. By the equality of the base angles of an isosceles triangle, angle OBC equals angle OCB, and angle OBA is equal to angle OAB. And the rest of that is pretty self-explanatory. It's not a very long proof. And then QED, I thought this was really neat, means, and I can't read Latin, so bear with me, quod erat demonstrandium, literally meaning what was to be shown, or thus it has been demonstrated. So that's basically how they would end their proofs. Pre-Socratic Greek school of philosophy, and Pythagoras had a lot of interesting ideas, a lot of them which he adopted from his teachers over time, but about reincarnation and about the universe and how it worked. But basically, Pythagoreanism is the assumption that numbers and mathematics constitute the true nature of things. And so within Pythagoreanism, there were two separate schools of thought. The acousmatikoi, or listeners, and they were focused more on the religious and ritualistic aspects of his teachings. And then the mathematikoi, or learners, who extended and developed the more mathematical work that he started. There was also a resurgence of Pythagoreanism, which is called Neo-Pythagoreanism in the 1st century BC. And Neo-Pythagoreans celebrate Pythagoras as the founder of Greek mathematics, which isn't really based on any historical documents or writings. So back to Pythagoreanism, as far as arithmetic and numbers go, they would represent numbers graphically and not symbolically. So they would use dots called Cephi, or pebbles, and they would make them into shapes like triangles or squares or rectangles or circles or pentagons. And this created this visual representation of numbers. And so that's why they were so easy to connect the numerical relationships and the geometrical exploration of those relationships. They also defined perfect numbers as those that were equal to the sum of all their divisors. So for example, one of those is 28, which is 1 plus 2 plus 4 plus 7 plus 14. And they talked about how the theory of odd and even numbers was central to arithmetic. And then in regards to geometry, they proved lots of simple geometrical theorems and came up with some interesting shapes. And that transition from dots to linear geometrical figures, in addition to Babylonian algebra and Pythagorean arithmetic, that all came to a place to make the basis for Greek geometric algebra. So I can't hardly talk about Pythagoras without talking about the Pythagorean theorem, which I'm sure you're all familiar with. A squared plus b squared equals c squared. And also Pythagorean triples, which are examples of numbers, natural numbers, let's say. So like 3, 4, and 5, or 5, 12, and 13. I'm sure some of you are familiar with, where the lengths of the sides of a right triangle, where all 3 sides have integer lengths. So here is 2 proofs, one on each side, that are algebraic. But if you actually go online and search for proof of Pythagorean theorem, you only land Pythagorean, not Pythagorean. You can find lots of different proofs and different strategies. I love algebra, so I wanted to do some algebraic proofs. So you can see how they took that middle triangle there, the ABC triangle, and they created 2 different squares and then calculated the area of each. And that's how they get c squared equals a squared plus b squared, which I thought was super interesting. And here are my sources.